I'll now be passing the floor over to Kristen Cowell, the lead sales engineer at Grundfos. Thank you so much for being here today, and I'll now pass it over to you to get started with your presentation.
I think it's a good afternoon and good evening to everybody by now. My name is Kristen Cole. I am the lead sales engineer for the aquaculture market from North America for Grundfos pumps. Going to speak to you a little bit today. We're going to take a highlight over some of the top 5 conditions that we see in aquaculture facilities that are inadvertently, I guess you could say, costing you money. So without that, for those of you, Grundfos is a name that's been known in pumps within aquaculture for quite some time due to our headquarters in Denmark. But for those of you that are not familiar with Grundfos, we are currently the #1 manufacturer of pumps in the world by number of units. We are also the #1 largest motor producer, also by units in the world. We're about 78 years old, and we have a global footprint through 83 divisions worldwide. So we have local presence within all of our major markets, but we do operate as one. We have one owner. Okay, so as sea-based operations are moving towards land and RAS, we have formed an aquaculture team to bring the more than 25 years experience that we have in aquaculture applications to the rest of the globe. The idea is to provide the same equipment that you're familiar with seeing in Norway, in Denmark, in Sweden, everywhere else in the globe, built to the standards, for instance, in North America with anti-flanges and NEMA motors. What we're seeing in a lot of these applications is pilot scale facilities are utilizing small, commonly available pumps from Amazon, Home Depot, pool suppliers, etc. However, as the facilities grow and the pumps get bigger and the piping gets more complex, attempts at direct scaling is now creating issues that the facilities hadn't seen in the past. And the bigger the pumps get, the bigger the chance for minor inconveniences and inefficiencies that were previously overlooked or inconsequential, becoming major cost sponges. Within the United States alone, we're spending a great deal, or I am spending a great deal of time addressing the industrialization of the operations within North America, as the rapid growth is leading a lot of aquaculture companies to utilize US-based engineering firms. And when they do that, we're seeing specifications built around typical North American water treatment standards, which for an aquaculture end user means the addition of excessive cost that does not impact the growth of the fish, nor does it starts to introduce requirements that are just not common to your industry. So when we take a step back at the 50,000-foot view, there are 5 major categories. Now, each of these categories, I could probably give you a 1-hour webinar, standalone webinar on each of these topics. So I'm going to go nice and high at a level that's approachable for whether you're an operator, an engineer, or an administrator. But it will be very quick, and I will hit on them pretty quickly. And then if any of these interest you or you'd like further analysis on them, you just need to let me know at the conclusion of the presentation. So operating cost number 1, this is the most obvious. This would be extended operation outside of your original design point. So are you operating your pump at the nameplate condition? Were your pumps originally selected for a future condition, i.e. when your construction's complete, not where you're at now? Are you using valves to trim your flow? And then are your valves always at some percent closed? So when a pump request comes into me, these are the things that I'm going to take a look at. Obviously, it's not an all-inclusive list, but when the inquiries come to me, I get the top 2. I get a flow and I get a head. And then I have to initiate much more extensive conversations. And the root behind these conversations and the questions that I ask are basically standard hydraulics. When you take a look at a pump curve, most people are looking at just their specified duty point. But there are almost 13 more critical variables when you're selecting a pump for an application. And this is where that extensive dialogue for aquaculture installations comes from, because your applications tend to be high flow, low head for your large recirculation applications, or lower flows, higher heads for some of your filter cleanout applications and similar. And none of the stuff shown on your screen right now takes into account piping impact. So that's another whole conversation in and of itself. So what I'm seeing when I go visit plants today, I see a pump selected by the engineers to operate where that orange star is located. However, when we actually look at where the pump is operating, it's operating at the red star because they have a valve installed to reduce the flow to their current state or to the demand of their plant. So my recommendation is if your plant's being commissioned in stages or subject to planning for future growth, your best bet may be to consider smaller, multiple smaller pumps with a multi-pump control scheme and then initiate those additional pumps as your flow increases rather than open a valve. And the reason behind that is you'll draw lower horsepower, you'll have a higher pump efficiency, and you'll have lower operating and maintenance costs. So again, if we revisit the list, flow and head, obviously critically important, but also what would be the operating range of your plant now, future, upset conditions, etc. And then is there sufficient NPSH? Not typically an issue with aquaculture because you have such large tanks, a lot of available head, but it's worth asking those questions. And then what we're going to come to next in the future topic is what is your operating control scheme? How is your actual operating today comparative to where you would like to go or changes in the future? So operating and maintenance costs impact number 2. This is your control scheme. Everybody gets scared within a lot of industries when we say controls. Why? Because in most people's minds, controls equals cost. However, I would like to change that point of view and have you think of controls limiting your cost and helping you keep your cost down. Now, why is this? This is because pumps are dumb, period. They're dumb. You're going to turn it on and it's going to produce a flow based on the back pressure it sees. You cannot manipulate your pump. So all you can do is manipulate your back pressure or manipulate the speed of your pump. And then there are small variables within the design of the pump itself, understood. But if we can utilize your control method, we can control operational and maintenance costs. So does this sound familiar? My pumps run at 100% and I vary the flow. And you can insert whatever equipment or tank here using this automated valve or a manual valve. When you say that to me, or when I walk through your plant and you point out the valve or I see that solenoid acting to control the valve, what I hear is, and what it means to your operations budget is, number 1, your pump and motor is most likely oversized. So you're at higher capital costs right off the front. Your pump is sized for losses through a valve at various stages of being open. So you're wasting electricity. Your pump may be operating outside its preferred operating range, which is going to lead to higher maintenance costs. You're paying for power even when it's not dictated by your process. So it's not helping the growth of your fish. It's not helping your recirculation operation. You're just paying for wasted power. So wasted operational costs. Your system maintenance costs are increased by the wear on the pump and the valves. Those valves aren't cheap and they're not fun to rebuild. Not necessary. Higher maintenance costs. So why not take a smaller pump and a smaller motor equipped with a VFD that is capable of taking that signal that you're currently sending to the valve and controlling your pump directly instead of controlling your valve. So when we talk about controls, a lot of people have and deal with pump control every day in their home. You have your household thermostat. You have a sump float switch. If you have a sump pump, a sump in your basement, your toilet float switch is a simple pump control. You have well pump controls if you have an on-site well. Our household is full of systems with pump controls. Yet for some reason, when you go to a traditional industrial system, our systems are overly simplified and people get scared of the controls. So we can break down pump controls into 4 levels. Level 1, manual on-off control, fixed speed. So I put power to my pump, it runs. Level 2, I'm going to add that same fixed speed, but I'm going to add that valve in, right? So now I'm going to take a signal from somewhere, whether that's level or flow, temperature, pH, any kind of a feedback signal. The one shown in front of you is a boiler level. but it doesn't matter. Whatever that signal is coming from that's going to control that feed valve is going to control how much of the water or media that is running through the line, and your system may or may not include a bypass. Level 3, I'm sorry. So preferred operating range. So if our customer specifies 9,000 gallons a minute at 178, so we're operating at that orange star. It falls nicely within the preferred operating range of this pump. That's that blue area right in the middle. And as a general rule, it's fair to say that in a majority of centrifugal pumps, the preferred operating range is about 70 to 120% of the best efficiency point. So at the peak of that efficiency curve, you take 70 to 120% of that, and that is a good ballpark of what your best efficiency point is. So now there's your best efficiency point in the green star. So now we take that same curve, and there's where our pump is designed for. And then we say, but we only want 3,000 gallons a minute. So we're going to utilize a valve to apply about 250 feet of head to slow down that pump to produce only 3,000 gallons, because the system doesn't need 9,000 gallons. When you do that, look how far outside of your best efficiency point you're now operating. So the results there are huge reduction in efficiency of your pump using a much bigger motor than you need to, and you're going to start to see wear on your pump and wear on your valve. And the thought that you want to put behind this is how much of that back pressure at that 3,000 gallons a minute is actually just lost through the valve. That's energy you're paying for. That's not helping you. Level 3 would be a variable frequency drive. So this is basically promoted frequently as at a VFD, it'll help you control your energy expense. A VFD is basically an intermediary between the electrical gate grid and your motor. It'll allow you to take advantage of the affinity laws, which is a design aspect of pumps. And that will help you get to a better relationship between the speed of your pump and the power that's required. For rotating equipment, typically power consumption is directly proportional to the cube of the speed, which means that by reducing the motor speed by 20%, you could produce energy savings of almost 50%. So now we're no longer going to run our pump at 100%. We're going to reduce our energy consumption by about 50% just by reducing the speed that the pump is operating. And when you look at that on a pump curve, like we've been seeing, you see the system curve there, and then the new operating point at the lower flow is the red star. These are the affinity laws. I could go into those. Those are way too deep for this presentation. Level 4 would be what I would consider the most complex, the most energy savings. So this would be combining a VFD with a PID or cascade controller through a PLC or a smart drive. Basically, we're taking a piece of a drive, a controller that knows that it's attached to a pump, that knows that it's attached to this specific model of a pump, and that this is the curve that it operates under. A VFD is dumb, just like the pump. The VFD doesn't know if it's attached to a conveyor belt, a pump, a compressor, or whatever. It's just going to vary the amount of electricity seen by your motor. So now we're going to add in some intelligence. Good example for this is a wash and clean application where the end user has a system where he wants to hose down tanks, he wants to flush his lines, he wants to dispense some foam, and then he has various hoses throughout the facility where he might have one hose running at a given time or two hoses running. And you can see those various colored spots that show this is a pump equipped with a very intelligent controller that is maximizing the efficiency for those 4 very different operating conditions. So a fun fact here, did you know that 65% of all pumps run at full speed all of the time, when typically their demand requires it only 5% of the time? So it's really taking a fine-tooth filter, let's say, and really looking at the application. So what does this mean to you as the end user? So if you go all the way to the level 4, where you're using a smart controller and a VFD, here's the comparison. So the red bar shows you a fixed speed pump operating with a pressure reducing valve. Just by applying a VFD and using constant pressure control, a standard backfit to the VFD, you're going to see about 28% savings in your energy consumption. By then adding in the smart controller, you're going to see an additional 7 to 10% savings. So as you can see there, there's about 20 to 30% savings you can get just by zeroing in on optimizing both your pump and how you're controlling it. Our next level is a simple one. It's a maintenance savings. Looking at the pump you're receiving, the pump that's being specified on your behalf, what is the bearing configuration on that pump? The most obvious to compare is a long coupled frame mounted design. It's a traditional ANSI model seen in the United States versus a closed couple, or what we call a split couple design. So the long mounted has a frame mount, has a grouted base that's required. It must be laser aligned after installation, routinely during operation, after any maintenance is performed. Each of those times you have a laser alignment, if you don't have a qualified technician on site, you're probably paying between $800 and $1,000 every time you need to align your piece of equipment. There are additional spares and lubrication. When you compare that to a closed couple design, it has a much smaller footprint. It doesn't require a base. It doesn't require grouting. It has lifetime alignment guaranteed. It's easily serviced by pulling the unit out of the back of the volute, and it has minimal spare parts required. The heads themselves are hydraulically the same. The performance and the efficiency is the same. The differences are strictly mechanical. And when it comes to operation of your plant, that's maintenance cost right there. Another fun fact, when we did a study, our service team, roughly only 7% of the measured machines fell within acceptable tolerances in a set that they measured over a given period of time. What does that mean to you, the end user? Numbers are great, but what misalignment means to the operation of your facility is you're going to have premature seal and bearing failures, which means your equipment goes down, which means you're no longer recirculating water. As that misalignment increases, you're also going to start to consume more energy. So how much energy it used to take to get you 3,000 gallons a minute is now going to take more energy for that motor to drive that wonky, off, misaligned shaft. Another random feature, doesn't affect cost, but it can affect your facility, is that close coupled units are space saving. Our space saving close coupled design has roughly a 35% smaller footprint than the same volume mounted in a long coupled format. The next one, and this is the great mystery. This is the one that I bring to your attention because of where a lot of land-based facilities are currently being located. They're placing plants on coastal locations at the end of the power grid, at the end of the distribution channel. And you're going to see why when I show you why this is important, that you are cognizant of the impact of your power quality on your facility. So is your power killing your pump and motors? Okay, so power is the amount of energy being consumed by an electrical device. If we think about it, we all think of water. The pressure in a hose is measured by volts as far as when you correlate it to power, and the flow of the water is measured by amps. So you have the current draw in amps times the voltage gets you to your power. A typical power distribution, you'll have a utility substation that feeds small neighborhoods, large neighborhoods, maybe some large businesses, and then there's your RAS plant sitting at the end of the distribution line on the shore. Outside temperature, about 75 degrees. The system is well operating, well balanced. What that means to your equipment in your plant, you have a 3-phase industrial motor coming in. You have about 20 amps coming in on each of your 3 phases, and you have a pretty balanced current. Everything's great in your facility. But what happens when the outside temperature increases to about 95 degrees? As all of the customers on the line start pulling greater amounts of electricity as they turn their AC on, and then that business starts turning on their AC and pulling a much greater load, you're now at the end of that distribution channel. And what that means to your pumps, as you can see in the description, lines 1 and 2 of your 3 phases are getting a lot of voltage pulled on them, or amperage pulled on them. So what you're seeing is what comes into your pump motors or motors other locations within your facility is your current's no longer balanced. So you can see there line 2 has a 24 amp measurement, and that results in an imbalance about 12.5%. As you do that, the motor windings within the motor are unbalanced and the magnets are being drawn more to one side than the other. What happens now is excessive heat and vibration. If we were to look at the actual measurements at your substation, you can see here, this is where they turned the AC on. And that's what's affecting your pump. So what does it mean to your pump? If your pump motor is operating on a voltage lower than its nameplate, it's pulling more current. So that excessive current is dissipated as heat, and heat kills pumps and motors. Your motor heats up, your shaft misaligns due to forces. Your motor shaft applies forces to the pump shaft, and then you start to see pump seal failures, pump bearing failures, escalating damage to your wet end, heat and misalignment to your pump internals, and then motor winding insulation will deteriorate and eventually short. Unfortunately, when you look at your pump, you're going to see this. Your failure is going to manifest itself as a seal failure, as a bearing failure. So you're going to think you have a pump problem when you have a power problem. So how do we detect power quality issues? So we have some power monitor devices for a couple $100. Not only it allows you to monitor the system consistently, but also it'll shut the pump down if the values exceed the set points. We can monitor 8 different variables within your energy supply. So that's power. Power is very important, which then feeds nicely into predictive maintenance. How do we predict when failures are going to happen? So here's the last major cost impact: emergency failures. Very obvious. So how much would your facility save if all of your repairs were planned? So we have what we call Grundfos Machine Health, which is a system of sensors and analysis for rotating equipment that allows us to reliably predict failures within equipment. So we have wireless vibration, temperature, and magnetic field sensors that are mounted on all the bearing locations on rotating equipment, and that send feedback to a centralized hub. And then a diagnosis occurs. So they combine millions of signals, constant signals coming from your machines, back to a computer, which analyzes and looks for anomalies. When anomalies are detected, it's sent to an actual expert person to analyze, a person who has lots of experience in vibration analysis, to analyze and verify that you have an issue. So an anomaly is detected, the fault is analyzed, and you're told what is going on in your device. It allows you to remedy the situation, and you go on through, can resume normal operation. And then if let's say the fault starts to become somewhat routine and repetitive, and then it allows you to predict a reoccurring issue and then identify it and address it. We have tons of case stories for this. This one is a board mill, which has nothing to do with fish, but it's just a good comment from a customer who said, within a week after the system went live, we started to see benefits. We immediately could work on tackling critical issues on critical machines. And that's why I thought this was important to mention. You don't have to wait for something to go wrong. It allows you to, even as you're establishing a baseline, realize there's something going on in your equipment before it becomes an issue. There's a long list of variables and features within your rotating equipment that can be diagnosed through this monitoring system. But the number one thing, the message to take home, is that it uncovers blind spots before they become emergencies. And then if you're of interest, the hardware itself. So we have the connectivity where you have the wireless sensors that speak to a hub. We have a diagnostic portal where they come in. And then the prescriptive insights is what you would see as a user via a dashboard and mobile alerts that are available to you. So in summary, the top 5 things, or the things that I want to kind of scratch at the back of your brain if you're having a pump problem within your facility, are pump selection. Are you operating where you were designed to operate? what type of pump you're specifying. Can you specify a better option to reduce your operational and your maintenance costs in the long term? Your pump control logic scheme. If you take one thing away from this presentation, I would like you to take home the thought to take a look at how you're controlling your pumps. It can save big money for a low investment and get you long-term operational savings. Power quality. If you're struggling with an issue that you can't identify that appears to be mechanical, take a step back and look at your power. And then lastly, is your facility large enough? Is downtime a critical feature or a critical problem within your facility? That predictive maintenance may be something that is worth investigating for your facility. So with that, that's what I have to present. Basically, in the end, at Grundfos, what we want you to do is, pumps are dumb. Pump technology has been around for hundreds of years, but hydraulics are hydraulics. And what we offer to you is the expertise to help you better design your controls and your pump selection to your actual application instead of generalizing. I can be reached at the email shown on the screen, and the Grundfos, we have 2 Grundfos websites shown at the bottom. One is our global website. You click on that, it'll direct you to your local website for our local language and product scope. And then the second one is our North American website as well.
Awesome.
Okay.
Thanks so much, Kristen. With the time we have left, just going to take a few questions from the audience, if that's okay. Now, the first one that I'm seeing here is, does Grundfos operate as a consulting firm? Could someone contact the company to help design their farm and purchase pumps from you?
So we don't design the farm in total. We work with consultants all the time. We would help you if you had an idea of what all your circulation flows are. We would help you select all the pumps that you would use. But if you needed help getting connected with a consultant that could do a consultancy that could do the plant as a whole, we could help refer you to people that we partner with all the time.
Awesome, thank you. What happens to closed coupled pumps when the seal fails?
Well, like all pumps, seal failures result in a leak, right? So a seal failure with a closed couple pump, you would just it's a simple clamshell coupling. You would undo that coupling and you would pull out your assembly, remove your impeller and replace your seal.
Okay, awesome. So you wouldn't have to replace the pump or anything in that situation?
Nope, you would just replace the seal itself.
Okay, perfect. Another one here. Do you offer pumps for small scale fish farms, or is it only intended for big RAS facilities?
Nope, we can do everything from small, I would want to say backyard systems, all the way up to thousands, tens of thousands of gallons a minute. So we can cover everything in between. So what I would recommend is just send us your conditions and we would select the right pump for you. But we definitely can go pretty small.
Perfect, awesome. Just so you know, I'm rifling through a bunch of great presentations and thank yous. So a lot of people love the presentation. How could you rectify problems caused by power quality, and what could you do to adjust your power quality?
Okay, so your power quality, one of the best things you can do is put in like a power quality monitor. Like I said, it's about $300. You wire it into your leads of the piece of equipment you're considering, and get yourself some feedback, get yourself some logging. So you have data. We work with you. We help you interpret that data. Then we would help you speak with your utility provider, right? So if you're a small facility that just has a substation outside of you and you're taking a 3-phase feed into your facility, it's going to come down to interacting with your utility. If you're a large scale facility that might have capacitor banks on its grounds, so you're taking much higher voltage and you're stepping it down on your facility, we would work with you and electricians to help you determine, is that the capacitor bank that's on my facility that's the problem, or is it what's coming from the utility? But it becomes a team effort, but it always is better to have that data and take that to your utility, because we've been through numerous cases where we make a claim to the utility without data, and they're like, no, we're fine, we got no alarms, blah, blah, blah. But if you actually have the data of what your facility is being fed, we start off at a better location.
Awesome. Thank you so much. I got time for one more here. Do these pumps work best with freshwater conditions?
No, we can do fresh, we can do salt, we can do brine, whatever you have. It's just gonna determine the materials of your wet end. So as you go up in temperature and salinity, you'll go to more, I won't say exotic materials, but you'll have to go to more corrosion resistant materials. If your budget doesn't allow for corrosion resistant metals, we do have a number of proven aquaculture coatings that we can use internally that allow us to get, similar life at lower cost.
Beautiful. Okay, awesome. Well, unfortunately, that is all the time that we have for today. So I just want to extend a very special thank you to Steiner and BioRouter and Kristen and Grundfos. Really appreciate the two of you taking time out of your day to present this for all of us. Thank you to those that asked questions and attended. I will see you all at the same time tomorrow for Standard BioTools and Hudex presentations. Thanks so much, everybody.
Thank you. Thanks, Alex.